Hi, and welcome back to another LeetCode problem. We're looking at the last sliding window problem in LeetCode.io's 150 list. So sliding window maximum is another hard problem. Now there are two solutions to it. One that is quite straightforward and should look very familiar when you have seen other sliding window problems. And then there's a little trick that will help bring down the runtime even further that I'm also going to show you. First, let's understand what we're looking at. So we're given an array integer nums, and there's a sliding window of size k, which is moving from the very left of the array to the very right. You can only see k numbers in the window. Each time the sliding window moves right by one position. And we're supposed to return the max sliding window. That is slightly confusing because we're actually supposed to return the maximum value of all the different sliding windows as we slide through the array, as you will see here now. Let me just copy this example, and we're going to put this here. Right. So as you can see here the sliding window. This is the first valid sliding window. The maximum value is 3. And the next one is also 3. Then in the third sliding window, it's 5. It's 5. Now it becomes 6 and 7. So this is the array that we are supposed to return here. So that'll be the output that is required. Now, if you've solved a couple of sliding window problems, you know that we're going to use an array, or preferably a deck that allows us to remove elements from the beginning and insert elements from the back, so that the insert and removal operations only take constant time. So in our first approach, that is actually what we're going to do. So we're going to use a deck, and we're going to compute the maximum of our window just with the max function, which will be an O of k operation. Now, we will end up with an O of n. N is the length of nums of n times k time, and we will need k places to store the sliding window. So let's implement that one real quick to get it out of the way. And while I'm doing that, I'm going to show you, and maybe you already seen this before, but I'm going to show you the general pattern for these sliding window problems. So it's always like this. You initialize the window. Then you iterate over the array or whatever the elements are. And then inside the iteration, so there will be for loops, inside the iteration, you update the window. Then you contract the window if it remains, if and only if the result is a valid window. And then finally you update the result if you have a valid window. That's kind of the logic that you always have in these sliding window approaches. So let's do this now for the naive approach. Well, the first thing is we're going to initialize our window, and we're going to use a deck, like I said. Importing the deck. And now we're going to just iterate over whatever our array is. So for I in range, well, actually, we're going to use a left pointer, right? We always have a pointer to the left index of our window and one that points to the right one. So for right in range length of nums, right? Now, how do we update the window? Well, we take the value at nums right, and we're going to add this to our window. Append, and we can make this a little simple. We just do it like so. Now we've updated our window. Now, how do we contract the window? Typically use a while loop. If you know that you only expand the window by 1, you could also use an if, but a while loop is typically the way to go. And so when should we contract? Well, in this case, we should contract as soon as the window grows too large, right? So if while length of window larger than k, well, what are we going to do? Well, we're going to do remove an element from window.pop left. Means we remove it from the left side. And we also typically have to update our pointer, our left pointer at this here, right here. Now, because we're using a deck, we don't really need to keep track of the left pointer, to be honest, right? But that would be part of the pattern. And now updating the result, well, we first check if it's a valid window, and that is the case if the length of the window is equal to k. Then we're going to append this to our result list. Sorry for the interruption. Result dot append, well, the maximum of our window. That's what we want to do. And this is an O of k operation, by the way. And yes, and in the end, we're just going to return the result. And of course, we need to initialize the result variable up here as well, equals this. So if you run this now, that should pass. And if we submit it, so this would be the O of n times k time and O of k space solution. We run into time limit exceeded. So that's typical for hard problems when we have a correct algorithm, but it's just not efficient enough. So yeah, so we probably need to rework this approach. And to do that, well, if you look at this example here again, is there a way that we can keep track of just what the maximum value is in this array? We just want to know what's the maximum, right? And we don't really care about anything else. So how can we make this an O of 1 operation to return the maximum? Well, it's difficult if we use, it's kind of difficult, right? Because we don't want to be sorting things, because that would increase the time actually to determine the maximum. If we want to use a heap, we could probably use a heap, but then inserting and removing elements from it would also be a log n operation. So n log k time, which might be a slight improvement, but we can take the idea of the heap, right? So if we always had the largest element of our array on top, so if we had the 3 in the first position and then everything else, that would be nice. And what we can do is, if we just keep track of the largest element, that means we have to know when to remove it. So if we associate the position of the largest element, so this would be at index 1, at index 1, at index 1. But when we see that, hey, our sliding window, it does not include 1 anymore, so that means we can remove the maximum element and we'll have a new element, right? So that could be the approach, and we can do that quite easily, I believe. Well, we could still keep our deck, and what we then do is when we insert a new maximum, and we always know that it has a position j that is larger than all the other elements in our deck, we could just remove all the elements that are smaller than 5. So we would remove those elements, and we only have 5 as the maximum element at the very front. And we know that we're only going to remove it once we run into the next largest element. So we have 5 in here, so this one wouldn't exist. That would have been removed. So 5 would be in the first element. Then we have a 3. Well, 3 is not larger than 5, so it's just going to be added here. But when we insert then the 6, it actually overrides the 3, so it gets removed as well. We could do that. We could also do it slightly different, where we say, okay, if 5 is our max element, then we have 3 and 6. When we pop out the 5, we pop out... No, we can't pop out the 3 because we don't know what's behind that. So yeah, so during insertion, we have to make sure that we remove all elements that are smaller and that are before. So that would be the approach with where we keep the deck, but we now only, well, now we make sure that in the first position we always have the maximum element for that. So how do we do that? Well, we still need to keep our deck, but we're going to put different elements into it, right? We're also not going to need the left pointer in this approach, but updating the window. So how do we do that? Well, we will do the following. So while we have something in the window, and window, like I said, at the last position has a value that is smaller than our num's right value. That means we're going to remove it. We're going to do window.pop. That's the removing of elements that are smaller that came earlier that are inside the window. And then finally we're going to append the current value, but also its index position, and that's at position right. Now we're going to contract the window, and for that we need to check whether it contains any elements, while window and while right minus the leftmost position of the window, right? And that is stored at window 0, so that's the head 1, right? The position as index 1, the value is at index 0. So if that is larger or equal than k, that means we can contract the window safely. And now finally, to update the results, all we need to check is if right plus 1 is larger or equal than k. That means it's guaranteed that our window is valid, right? We made sure that during contraction, it has the right size. And now we just need to check of whether, where are we? Are we at index 0 or the index, right? The window up to here is not valid, up to here is not valid. But once we reach all 3, then it becomes valid. So this is what this if statement checks. Now, instead of appending the max window, all we need to do is, we need to append the first element that's in the window. So that's at position 0 and 0. And now that becomes an O of 1 time thing, and our time and space complexity is going to be O of n and O of k space in the worst case. O of n because we're still iterating over all of the elements in the array, and likewise with the window contraction, that means we're only going to contract it O of n times in total as well. Right, typo, result, logic, okay, let's see that. And we're going to submit it, see if it passes all of the tests. And there you have it. So now you know how to determine the optimal solution. And the trick here is really to figure out how to have access to the maximum element by using this little trick with the deck. Yeah, that's it. Thanks very much.